Tonight on The Sleepy Scientist, we're drifting gently through the quiet darkness of space to explore one of the most mysterious visitors our solar system has ever received, 3I Atlas. The enigmatic comet that has raised profound questions about the nature of interstellar objects. From its distant origins in the void between stars to the surprising discoveries made by the Hubble Space Telescope, we'll journey through a cosmic mystery that continues to whisper secrets about our universe. In the gentle silence of space, light travels for years between destinations. There exists a population of cosmic wanderers that drift between the stars, like messages in bottles thrown into an infinite ocean. These interstellar visitors carry with them the stories of distant worlds, foreign solar systems, and the vast spaces that separate one stellar neighborhood from another. Tonight we turn our peaceful attention to one such visitor, mysterious object designated 3I Atlas, which has challenged our understanding of what these cosmic travelers truly are. As we begin our gentle exploration, let us first breathe in the wonder of discovery. The Hubble Space Telescope, that faithful sentinel of space, has turned its sensitive eye toward this distant visitor and found something unexpected. In the quiet language of scientific observation, Hubble has whispered to us revelations that have left astronomers puzzled, excited, and deeply curious about the nature of our universe's traveling companions. The story of 3I Atlas is not just the story of a single object drifting through space. It is a gentle meditation on the interconnectedness of all things cosmic. A reminder that our solar system exists within a vast galactic community where objects regularly travel between stellar homes. In the soft glow of distant starlight, we find ourselves part of a cosmic dance that spans light years and millennia, where every visitor from the void brings with it the potential to revolutionize our understanding of how the universe works. Tonight's journey will take us slowly and peacefully through the discovery of this mysterious object, the surprising observations made by Hubble, and the profound questions that these discoveries have raised about the nature of interstellar space and the objects that traverse it. We'll explore how 3I Atlas fits into the growing catalog of interstellar visitors, what makes it unique among cosmic wanderers, what its presence in our solar system tells us about the greater universe beyond our stellar neighborhood. In the gentle tradition of scientific exploration, we'll approach these mysteries with wonder rather than urgency, curiosity rather than anxiety. The cosmos has spent billions of years crafting these cosmic messengers, and we can afford to take our time understanding their quiet revelations. As we drift through the data and observations, we'll discover that sometimes the most profound scientific questions arise not from what we find, but from what we fail to understand about what we found. So settle in comfortably as we prepare to embark on this peaceful journey through space and time, following the trail of 3I Atlas from its mysterious origins to its surprising revelations. In the quiet darkness of our cosmic exploration, we'll find that the universe still holds many gentle surprises for those patient enough to listen to its whispered secrets. The peaceful pre-dawn hours of December 29, 2019, while most of the world slept, a pair of robotic telescopes in Hawaii began their nightly dance of cosmic surveillance. The Asteroid Terrestrial Impact Last Alert System, known gently by its acronym ATLAS, swept its mechanical gaze across the star-filled sky, searching for objects that might pose a threat to Earth. In the quiet, methodical way that automated systems conduct their work, ATLAS captured light that had traveled across vast distances of space, light that carried within it the signature of something extraordinary. The discovery was not dramatic in the way that movies portray scientific breakthroughs. There were no alarms, no sudden exclamations of eureka, no running through hallways with printouts of data. Instead, the discovery of 3I Atlas was as gentle as the object itself, a small point of light moving against the background of stars. Captured in the electronic memory of a CCD camera and flagged by software designed to notice things that move where they shouldn't, initially designated C2019Y1. This faint smudge of light appeared unremarkable among the thousands of asteroids and comets that astronomers catalog each year. But as observations continued and orbital calculations were refined, something extraordinary became apparent. The trajectory of this object was hyperbolic. It was moving too fast to be gravitationally bound to our sun. This quiet visitor was not a permanent resident of our solar system, but rather a traveler from the vast spaces between the stars. The realization that 3IATLAS was an interstellar visitor filled the astronomical community with a gentle excitement. Only 2 confirmed interstellar objects had been discovered before this moment: the enigmatic Oumuamua in 2017 and the more comet-like 2I Borisov in 2019. Each of these cosmic visitors had provided unique insights into the nature of interstellar space and the populations of objects that drift between stellar systems. Now, with the discovery of 3IATLAS, humanity had its 3rd confirmed messenger from the void. The process of confirming an interstellar origin requires patience and precision. Astronomers must track the object for weeks or months, carefully measuring its position against the background stars. They calculate its orbital elements, determining the shape and orientation of its path through space. A truly interstellar visitor will have an orbital eccentricity greater than 1.0, indicating a hyperbolic trajectory that will carry it back out into the void from whence it came. For 3IATLAS, these calculations revealed an orbital eccentricity of approximately 1.4, confirming its interstellar nature. But unlike its predecessors, 3IATLAS presented astronomers with a puzzle that would deepen as observations continued. Initial estimates suggested it was a comet, showing the characteristic fuzzy appearance or coma that develops when a comet's ices begin to sublimate as it approaches the sun. Yet, there were subtleties in its behavior and appearance that didn't quite fit the standard model of cometary activity. The gentle mystery of 31ATLAS began to unfold as astronomers around the world turned their telescopes toward this distant visitor. Each observation added another piece to a puzzle that seemed to become more complex rather than clearer. The object's brightness varied in ways that suggested it was rotating, tumbling slowly through space, like a cosmic football thrown across the galaxy. Its spectral signature, the fingerprint of light that reveals an object's composition, hinted at its materials and processes that challenge simple explanations. What made 3I Atlas particularly intriguing was its timing and trajectory. Unlike Oumuamua, which was discovered as it was already leaving the inner solar system, 3I Atlas was caught on its way in. This provided astronomers with a precious opportunity to study an interstellar visitor as it approached the sun. Watching how it responded to increasing solar radiation and gravitational influence, it was like having a front row seat to observe how a messenger from another star system behaves in the environment of our own stellar neighborhood. The discovery teams, led by astronomers Larry Deneau and Robert Warwick at the University of Hawaii, found themselves the custodians of humanity's 3rd confirmed visitor from interstellar space. Their careful observations and calculations had revealed not just another asteroid or comet, but a cosmic time capsule that had traveled for potentially millions of years through the cold darkness between stars to arrive in our solar system. At this particular moment in time, as word of the discovery spread through the astronomical community, observatories around the world began to coordinate their efforts to study 3IATLAS, the Hubble Space Telescope. With its unparalleled ability to observe faint objects with exquisite detail, was among the first major observatories to turn its attention to this mysterious visitor. Little did astronomers know that Hubble's observations would reveal surprises that would fundamentally challenge their understanding of what 3IATLAS actually was. In the quiet, methodical way that science advances, the discovery of 3I Atlas represented both an end and a beginning. It was the culmination of years of automated sky surveys designed to catalog potentially hazardous asteroids. But it was also the beginning of a new chapter in our understanding of interstellar visitors and the populations of objects that wander between the stars. Each new interstellar discovery adds to our growing appreciation of how interconnected the galaxy truly is, and how our solar system exists. It's just one harbor in a vast cosmic ocean traveled by countless wandering worlds. High above Earth's atmosphere, in the serene darkness of space, The Hubble Space Telescope maintains its patient vigil among the stars. For more than 3 decades, this remarkable observatory has served as humanity's most sensitive eye on the cosmos, peering through the clear vacuum of space to observe celestial objects with a clarity impossible from Earth's surface. When astronomers requested that Hubble turn its attention to the mysterious 3I ATLAS, they were calling upon one of the most sophisticated scientific instruments ever created to help solve a cosmic puzzle. The Hubble Space Telescope represents the culmination of human ingenuity applied to the gentle art of cosmic observation. Its 2.4-meter primary mirror is polished to perfection and free from the distorting effects of Earth's atmosphere, can detect objects billions of times fainter than what the human eye can see. When this magnificent instrument focuses on a target, it can reveal details and subtleties that often surprise even experienced astronomers who think they understand what they're looking at. Observing 3.1 Atlas with Hubble required careful planning and precise timing. Interstellar visitors don't linger in our solar system. They follow their hyperbolic trajectories with the inexorable precision of celestial mechanics, peering briefly in our cosmic neighborhood before continuing their journey back into the void. Astronomers had a limited window of opportunity to study this mysterious object while it was close enough and bright enough for detailed observation. The process of scheduling Hubble observations is itself a gentle dance of priorities and possibilities. Thousands of astronomers around the world compete for time on this precious instrument, arguing for the scientific importance of their particular cosmic target. The case for observing 3I Atlas was compelling. Here was only the 3rd confirmed interstellar visitor ever discovered. It was displaying behaviors that didn't quite fit existing models of cometary activity when Hubble's observations of 3I Atlas began in early 2020. The telescope employed its full suite of sophisticated instruments. The Wide-Field Camera 3, with its ability to capture both visible and near-infrared light, would reveal the object's color and composition. The Space Telescope imaging spectrograph would analyze the specific wavelengths of light reflected and emitted by 3IAS, providing clues about its surface materials and any gases surrounding it. The beauty of Hubble's observations lies not just in their precision, but in their patience. Unlike ground-based telescopes that must contend with Earth's rotation and atmospheric conditions, Hubble can maintain its steady gaze on a target for hours or even days. This stability allows for the accumulation of photons, those fundamental particles of light that carry information across vast distances of space, building up detailed images and spectra that reveal the secrets of distant objects. As data from Hubble began to flow back to Earth, astronomers found themselves looking at images and measurements that challenged their initial assumptions about 3IATLAS. The telescope's exquisite sensitivity revealed structures and behaviors that weren't immediately obvious from ground-based. What they saw would eventually lead to a fundamental reinterpretation of what kind of object 3.1 ATLA actually was. The technology that makes Hubble's observations possible represents decades of advancement in detector technology, optics, and spacecraft engineering. Charge-coupled device CCD cameras can record individual photons with quantum efficiency approaching 90%, meaning that almost every particle of light that reaches the telescope contributes to the scientific data. This extraordinary sensitivity allows Hubble to observe objects so faint that they would be completely invisible to even the largest ground-based telescopes. Hubble's unique vantage point above Earth's atmosphere eliminates the twinkling and blurring effects that plague ground-based astronomy. In the steady darkness of space, stars appear as perfect points of light, and faint extended objects like cometary Comet can be studied with unprecedented detail. For an object like 3I ATLAS, which was already challenging to observe due to its distance and faintness, Hubble's capabilities were essential for revealing its true nature. The process of converting Hubble's raw observations into scientific understanding requires sophisticated analysis techniques developed over decades of space-based astronomy. Each image must be calibrated, corrected for instrumental effects, and carefully processed to extract the maximum amount of scientific information. The gentle art of astronomical image processing reveals details that are often invisible in the raw data, bringing to light the subtle signatures that distinguish one type of cosmic object from another as astronomers worked with Hubble's data on 3I Atlas. They employed photometric techniques to measure the object's brightness variations, spectroscopic analysis to determine its composition, and astrometric measurements to refine its orbital trajectory. Each of these approaches contributed to a growing understanding that 3I Atlas was not quite what it had initially appeared to be. The telescope's observations were revealing an object that defied simple categorization, challenging astronomers to think more carefully about the diversity of interstellar visitors. The collaborative nature of Hubble observations reflects the international spirit of modern astronomy. Scientists from institutions around the world contributed to the study of 3I Atlas, bringing together expertise in orbital mechanics, spectroscopy, planetary science, and stellar astronomy. This gentle cooperation across national boundaries and institutional affiliations represents science at its best, the collective human effort to understand our cosmic environment. Hubble's observations of 3I Atlas were conducted during a particularly interesting phase of the object's journey through our solar system. As it approached its closest point to the Sun, increasing solar radiation was causing changes in its appearance and behavior. The telescope was able to monitor these changes in real time, providing astronomers with a dynamic picture of how an interstellar visitor responds to the environment of our solar system. The data quality achieved by Hubble's observations was extraordinary, even by the telescope's own high standards. The combination of perfect seeing conditions in space, sophisticated instrumentation, and careful observation planning resulted in measurements of unprecedented precision for such a faint and distant object. These observations would provide the foundation for discoveries that would challenge fundamental assumptions about the nature of interstellar objects and the processes that shape them during their long journeys through space. As the initial excitement of discovering another interstellar visitor began to settle into the methodical rhythm of scientific observation, 3I Atlas revealed itself to be an object that defied easy categorization. In the gentle tradition of cosmic mysteries, this distant wanderer presented astronomers with a collection of observations that didn't quite fit any single explanation. It's like a puzzle with pieces from different boxes. 3I Atlas challenged scientists to expand their understanding of what interstellar objects could be. The first clue that 3I Atlas was unusual came from its brightness behavior. Most comets follow predictable patterns as they approach the Sun. Their surfaces heat up, ices sublimate, and they develop the characteristic fuzzy appearance of a cometary coma. The brightness typically increases in a smooth, well-understood manner that allows astronomers to predict how visible a comet will become. But 3I Atlas didn't follow this script. Its brightness variations were erratic, sometimes brightening rapidly, only to fade again in ways that puzzled experienced comet observers. Spectroscopic observations, the gentle art of spreading an object's light into its component colors to reveal its composition, added another layer to the mystery. When astronomers analyzed the spectrum of 3I Atlas, they found signatures that were subtly different from typical comets. The ratios of different gas species in its coma didn't match the standard model of cometary composition. It was as if this visitor from interstellar space had been shaped by different processes or carried different materials than the comets that call our solar system home. The physical size of 3I Atlas proved to be another puzzle. Initial estimates suggested it was relatively small, perhaps a few hundred meters across, but the exact dimensions were difficult to determine. Unlike asteroids which reflect sunlight from solid surfaces, 3I Atlas was surrounded by a diffuse coma of gas and dust that made it challenging to distinguish between the actual nucleus and the surrounding material. This uncertainty in size contributed to the difficulty in understanding its true nature. As observations continued, astronomers noticed that 3I Atlas seemed to be undergoing some kind of evolutionary change. Its appearance in images taken weeks apart showed subtle differences that suggested the object was not stable. This evolution was particularly intriguing because it was happening as the object was still relatively far from the Sun, where solar Heating should have been minimal. Something else was driving the changes in this mysterious visitor. The orbital characteristics of 31ATLAs added another dimension to its mystery. While its hyperbolic trajectory clearly identified it as an interstellar visitor, the specific details of its orbit provided clues about its origin and journey. By tracing its path backward through space and time, astronomers could estimate where it might have come from in the galaxy. But unlike some interstellar visitors that seem to arrive from specific directions related to local stellar motions, 31ATLA's trajectory was more ambiguous, making its ultimate origin difficult to determine. The rotation period of 3I Atlas, determined from its brightness variations as it tumbled through space, revealed another interesting characteristic. The object appeared to be spinning relatively slowly compared to many asteroids and comets, completing one rotation every several hours. This slow rotation suggested either a fairly large object or one with an unusual shape, possibly elongated, like a cosmic football tumbling end over end through the void. Temperature measurements of 3IATLAS, obtained through observations at infrared wavelengths, provided additional clues about its composition and behavior. The object's thermal characteristics didn't quite match those of typical solar system comets, suggesting differences in surface properties or internal structure. These subtle thermal signatures hinted at materials or processes that were unfamiliar to astronomers accustomed to studying objects that formed in our own solar system. The dust production rate of 3I Atlas was another source of scientific curiosity. While clearly active like a comet, producing the gas and dust that created its visible coma, the rate and pattern of this activity were unusual. The dust grains themselves, when analyzed through polarimetric observations, showed properties that were subtly different from those typically found in solar system comets. It was as if the interstellar environment had somehow modified these materials during their long journey through space. Perhaps most intriguingly, 31 Atlas seemed to be responding to solar radiation in ways that weren't entirely predictable. The relationship between its distance from the sun and its brightness and activity level showed irregularities that suggested complex processes were occurring on or within the object. These processes might involve exotic ices that sublime at different temperatures than water ice, or perhaps structural changes within the object itself as it responded to the alien environment of our solar system. The color of 3IATLAS, measured through careful photometry at multiple wavelengths, provided another piece of the puzzle. The object appeared slightly redder than typical solar system comets, a characteristic that could indicate either differences in surface composition or the effects of prolonged exposure to cosmic radiation during its interstellar journey. This subtle coloration was consistent with materials that had been processed by the harsh environment of interstellar space over geological timescales. As astronomers compiled these various observations into a coherent picture, they found themselves confronting the possibility that 3I Atlas represented a new type of interstellar object. It was clearly active like a comet, but its behavior and characteristics didn't match the standard cometary model. It might be a fragment of a larger object that had broken apart during its interstellar journey, or perhaps it represented a class of objects that form under different conditions than those found in our solar system. The mystery of 3IATLAS reminded astronomers that the universe is full of objects and processes that challenge our Earth-based perspective on cosmic phenomena. Each interstellar visitor brings with it the opportunity to learn something new about the conditions and processes that exist in the vast spaces between stars. In the gentle humility that comes with scientific discovery, researchers began to realize that 3I Atlas might be teaching them that their understanding of comets and interstellar objects needed to be expanded to accommodate the rich diversity of cosmic wanderers that populate our galaxy. Until 2017, the concept of interstellar visitors to our solar system existed primarily in the realm of theoretical possibility. Astronomers had long suspected that objects occasionally escaped from other stellar systems and wandered through the galaxy, but none had been definitively detected. The discovery of Oumuamua changed everything, opening our eyes to a population of cosmic wanderers that had been passing through our neighborhood all along, invisible to our technology and unrecognized for what they truly were. Oumuamua, whose Hawaiian name means scout or messenger from afar, was humanity's first confirmed visitor from interstellar space. Discovered by the Pan-STARRS telescope in October 2017, his elongated object immediately captured the attention of astronomers with its unusual characteristics. Unlike any asteroid or comet previously observed, Oumuamua showed no signs of cometary activity yet exhibited non-gravitational acceleration as it left our solar system. Leading to intense scientific debate about its nature and composition, the discovery of Oumuamua revolutionized our understanding of interstellar space. Suddenly, astronomers realized that the void between stars was not as empty as previously thought. If one interstellar visitor could be detected during its brief passage through our solar system, there must be countless others following similar trajectories, most too small or distant to be observed with current technology. The galaxy began to seem less like a collection of isolated stellar systems and more like a vast ocean with currents of wandering objects flowing between the stars. 2 years after Oumuamua's discovery, amateur astronomer Gennady Borisov detected another interstellar visitor using a telescope he had built himself. Designated to I. Borisov, this object was more comet-like in its behavior, showing clear signs of outgassing and developing a proper cometary coma as it approached the Sun. Borisov provided astronomers with their first opportunity to study a normal interstellar comet, one that behaved much like the comets native to our own solar system. The study of I. Borisov revealed fascinating insights about the universality of planetary formation processes. Spectroscopic analysis showed that its composition was remarkably similar to comets from our own Oort cloud, suggesting that the processes that create and shape comets might be similar throughout the galaxy. This discovery provided comfort to astronomers who wondered whether objects from other stellar systems might be completely alien in their characteristics and behavior. With the discovery of 3I Atlas, astronomers now had 3 confirmed interstellar visitors to compare and contrast. Each object told a different story about the conditions and processes that exist in interstellar space and other stellar systems. Oumuamua remained enigmatic and unusual. Borisov appeared comfortingly familiar, and 3I Atlas presented new puzzles that didn't fit neatly into either category. The growing catalog of interstellar visitors began to reveal the diversity that exists among these cosmic wanderers. Just as the asteroids and comets of our own solar system show tremendous variety in their sizes, compositions, and behaviors, interstellar objects appeared to encompass a similar range of characteristics. This diversity suggested that planetary formation and evolution processes throughout the galaxy produce a rich population of small bodies that can escape their home systems and wander between the stars. The detection rate of interstellar visitors provided important constraints on their population and frequency. Based on the 3 confirmed detections and the limited observational capabilities that discovered them, astronomers estimated that dozens of interstellar objects might pass through the inner solar system each year. It's most too small or faint to be detected. This realization transformed our understanding of the solar system from an isolated island in space to a busy harbor visited regularly by travelers from distant shores. The study of interstellar visitors also opened new avenues for understanding galactic evolution and stellar system interactions. These objects serve as samples from other stellar systems, carrying with them information about the conditions and processes that shape their formation. By studying their compositions, structures, and behaviors, astronomers can learn about planetary formation processes and environments very different from our own solar system. The implications for astrobiology are particularly intriguing. If interstellar objects can carry material from one stellar system to another, they might serve as a mechanism for distributing organic compounds or even microbial life throughout the galaxy. While the harsh conditions of interstellar space make this scenario challenging, it remains a possibility that adds an exciting dimension to the search for life beyond Earth. The technological requirements for detecting and studying interstellar visitors have driven advances in astronomical surveys and observation techniques. Projects like LINER, NEOEYES, Pan-STARRS, and ATLAS were originally designed to detect potentially hazardous asteroids, but they have proven equally valuable for discovering interstellar visitors. The upcoming Vera Rubin Observatory promises to revolutionize this field by detecting interstellar objects at an unprecedented rate. Each interstellar visitor discovered so far has required intensive follow-up observations to confirm its nature and study its characteristics. The brief time these objects spend within range of our telescopes means that astronomers must act quickly to gather as much data as possible before the visitors fade back into the darkness of space. This urgency has fostered new levels of international cooperation and rapid response. Observation protocols. The nomenclature system for interstellar objects reflects their special status in astronomy. The I designation indicates an interstellar origin, distinguishing these visitors from the asteroids and comets that belong to our solar system. The numbering system acknowledges them as a distinct class of objects worthy of separate classification, recognizing their importance for understanding galactic processes and stellar system interactions. Theoretical models of interstellar object populations suggest that the galaxy might contain billions of these wandering worlds, ejected from their home systems during the chaotic early phases of planetary formation or through gravitational interactions with passing stars. Most of these objects are probably small, rocky, or icy bodies, but some might be larger, even planet-sized objects wandering alone through the cosmic dark. The study of interstellar visitors has also provided insights into the dynamics of our own solar system. By understanding how objects can be ejected from stellar systems and how they behave during their interstellar journeys, astronomers can better understand the processes that shaped our own collection of planets, asteroids, and comets. The visitors serve as natural experiments in planetary dynamics and evolution, showing us what happens when familiar processes operate under different conditions. As the field of interstellar object research continues to develop, preparing for a future in which such discoveries become routine rather than exceptional. New telescopes and survey programs will detect these visitors in ever-increasing numbers, building up a statistical sample that will allow detailed studies of their population characteristics and origins. What began as surprising individual discoveries is evolving into a new branch of astronomy, focused on understanding the galactic community of wandering worlds. As Hubble's detailed observations of 3I Atlas began to be analyzed and interpreted, astronomers found themselves confronting data that challenged their fundamental assumptions about what this interstellar visitor actually was. The high-resolution images and precise measurements reveal behaviors and characteristics that didn't fit neatly into any existing category of solar system object. In the gentle way that science advances through puzzles and contradictions, 3I Atlas was raising questions that would require astronomers to reconsider their understanding of interstellar visitors and the processes that shape them. The first major surprise came from Hubble's ability to resolve fine details in the structure of Zebel 3.1 Atella S's coma. While ground-based telescopes had detected the fuzzy appearance characteristic of an active comet, Hubble revealed that the coma had an unusual asymmetric structure, instead of the roughly spherical halo of gas and dust typically seen around comets. 3.1 ATLAS showed directional features and irregular patterns that suggested more complex processes were at work than simple sublimation of surface ices. Even more puzzling was the temporal evolution of these structures. As Hubble continued to monitor 3I Atlas over several weeks, the telescope captured changes in the coma's appearance that occurred on surprisingly short timescales. Features appeared and disappeared, brightened and faded, in patterns that didn't match the predictable behavior expected from a comet gradually warming up as it approached the sun. It was as if the object was undergoing some kind of episodic or catastrophic process rather than the steady evolution typical of solar system comets. The spectroscopic data from Hubble added another layer of mystery. While initial observations had suggested that 3I Atlas was producing water vapor like a typical comet, more detailed analysis revealed unusual ratios of different molecular species. The relative abundances of water, carbon monoxide, carbon dioxide, and other gases didn't match the patterns seen in solar system comets, suggesting either a different formation environment or different evolutionary processes during its interstellar journey. Perhaps most dramatically, Hubble's observations began to reveal that 3I Atlas might not be a single intact object at all. The telescope's exquisite resolution detected what appeared to be multiple distinct sources of brightness within the coma, suggesting that the comet might actually be a collection of fragments traveling together. This possibility raised profound questions about what had happened to 3I Atlas during its journey through interstellar space or upon entering our solar system. The implications of a fragmenting interstellar visitor were staggering. 3I Atlas was indeed breaking apart. Astronomers were witnessing a process that might be common among interstellar objects, but had never been observed before. The fragmentation might be caused by thermal stresses as the object warmed up in our solar system. Or it might be the delayed result of some catastrophic event that occurred during its long journey between the stars. The discovery of possible fragmentation also raised questions about the nature of interstellar objects in general. How many of the objects classified as single interstellar visitors might actually be fragment streams or debris fields? Could the unusual characteristics of Oumuamua be explained by similar fragmentation processes? The possibility that interstellar visitors might commonly break apart as they pass through solar systems added a new dimension to their study and interpretation. Another puzzling aspect of 3I Atlas revealed by Hubble's observations was its apparent size and density. Based on the brightness and thermal characteristics of the object, astronomers calculated that it should be quite small, perhaps only tens of meters across. But an object this small would typically be held together by weak gravitational forces, making it surprising that it could survive the journey through interstellar space and the thermal stresses of approaching our Sun without fragmenting completely. The surface properties of 3I Atlas also defied easy explanation. Hubble's photometric observations revealed color variations across the object and its coma that suggested heterogeneous composition or variable dust properties. This variability was inconsistent with a simple model of a uniform icy nucleus surrounded by a symmetric coma, indicating that the processes operating on 3I Atlas were more complex than initially assumed. The orbital dynamics of 3I Atlas presented additional mysteries. While its hyperbolic trajectory clearly identified it as an interstellar visitor, subtle variations in its motion suggested that non-gravitational forces were affecting its path through space. These forces, likely related to outgassing from its surface, were stronger and more variable than expected for an object of its estimated size and composition. The timing of 3I Atlas's activity also raised questions. Most comets become active as they approach the Sun, and surface ices begin to sublimate due to solar heating. But 3I Atlas showed signs of activity while still relatively far from the Sun, suggesting either the presence of highly volatile materials that sublimate at very low temperatures, non-thermal processes driving the observed outgass. As astronomers grappled with these observations, they began to realize that 3I Atlas was challenging fundamental assumptions about how interstellar objects should behave. The standard model of comets as relatively pristine icy bodies formed in the outer regions of stellar systems might not apply to objects that have spent millions or billions of years traveling through the harsh environment of interstellar space. The questions raised by 3I Atlas extended beyond the object itself to broader issues about the population and characteristics of interstellar visitors. If this visitor was fragmenting or behaving unusually, what did this mean for interpreting observations of other interstellar objects? How many seemingly single objects might actually be debris streams or fragment clusters? What processes operate during the long journey through interstellar space that might modify the original properties of these cosmic wanderers? The case of 3I Atlas also highlighted the importance of rapid, detailed follow-up observations for interstellar visitors. Because these objects pass through our solar system only once, astronomers have a limited window of opportunity to study them before they fade back into the darkness of space. The surprising discoveries made about 3I ATLAS emphasized how much can be learned from intensive observation campaigns using the most sophisticated available instruments. Perhaps most importantly, 3I Atlas was teaching astronomers about the limits of their current understanding and the gentle humility that comes with encountering the unexpected. Researchers began to appreciate that the universe of interstellar objects might be far more diverse and complex than they had previously imagined. Each new discovery was expanding the catalog of possibilities for what these cosmic visitors could be and how they might behave during their brief passage through our solar neighborhood. To understand the mysteries presented by 3I Atlas, we must first embark on a gentle journey backward through space and time, tracing its path from our solar system to its distant origins in the void between stars. This cosmic wanderer has traveled for eons through the cold darkness of interstellar space, carrying with it the stories of distant worlds and the scars of its long journey through the galaxy's most desolate regions. The journey of 3I ATLAS likely began millions or perhaps billions of years ago in a stellar system far from our own. Like countless other small bodies throughout the galaxy, may have formed in the outer regions of its birth system, where temperatures were cold enough for water and other volatile compounds to condense into solid ice. In those distant reaches, where starlight was dim and planetary formation was a chaotic dance of gravitational forces, 3I ATLAS took shape as one of billions of icy worlds orbiting its parent star. The mechanism that ejected 3I ATLAS from its home system remains a mystery, but astronomers have identified several processes that can liberate small bodies from their stellar neighborhoods. Gravitational encounters with passing stars can perturb the orbits of objects in a system's outer regions, sending some spiraling inward toward their star and others flying outward into the void. The formation of giant planets can also scatter smaller bodies, with some achieving the escape velocity necessary to leave their system forever. Perhaps 3I Atlas was expelled during the violent early phases of planetary formation in its birth system, when collisions between planetesimals and the migration of giant planets created chaos in the outer reaches of the disk. Or maybe it was dislodged much later by the close passage of another star, a gravitational interaction that reached across light years to pluck this small world from its comfortable orbit, fling it into the cosmic wilderness. Once liberated from its home system, 3I ATLAS began its long drift through the galaxy. The interstellar medium is not truly empty. It contains roughly 1 atom per cubic centimeter, along with dust grains, magnetic fields, and occasional denser clouds of gas and dust. For a small object like 3I ATLAS, traveling at speeds of tens of kilometers per second, these encounters with interstellar material would have gradually modified its surface properties and composition. The cosmic radiation environment of interstellar space is harsh and unforgiving. High-energy particles from distant stars and supernova constantly bombard objects traveling through the void, breaking down organic molecules and altering surface chemistry. Over millions of years, this radiation processing would have created a darkened, radiation-modified surface layer on 3I Atlas, fundamentally changing its optical and thermal properties from its original pristine state. During its interstellar journey, 3I Atlas would have experienced temperature extremes that no object in our solar system ever encounters. Far from any star, its surface temperature would have dropped to just a few degrees above absolute zero, causing materials to become incredibly brittle and prone to fracturing. Thermal cycling as it passed near other stars or through regions of varying stellar density might have created internal stresses that weaken the object's structural integrity. The gravitational environment of interstellar space also differs dramatically from the stable conditions within a solar system. While the overall gravitational field of the galaxy provides a gentle guiding force, 3I Atlas would have experienced countless small perturbations from passing stars, molecular clouds, and other massive objects. These interactions would have gradually modified its trajectory, sending it on a complex path through the galaxy that eventually led to its encounter with our solar system. Micrometeorite impacts during its interstellar journey would have gradually eroded the surface of 3I Atlas, creating a layer of fragmented material and potentially exposing fresh ices beneath. The impact rate in interstellar space is much lower than within a solar system, but over geological timescales. Even rare impacts can accumulate to create significant changes in a small object's structure and composition. As 3I Atlas wandered through the galaxy, it may have passed through regions of space with very different conditions. Dense molecular clouds could have provided temporary shielding from cosmic radiation, while subjecting the object to different chemical environments. Passages near active stellar regions might have exposed it to intense stellar winds and radiation fields, while journeys through the sparse halo regions of the galaxy would have provided a more benign environment. The magnetic field structure of the galaxy would have guided charged particles in 3I Atlas's vicinity, creating complex patterns of radiation exposure that varied with the object's galactic location and motion. These variations in the radiation environment might explain some of the unusual compositional characteristics observed in interstellar visitors. Different regions of space would have processed their surface materials in different ways. The approach of 3I Atlas to our solar system marked the end of its long interstellar exile and the beginning of its brief encounter with stellar warmth and gravitational order. As it entered the outer reaches of our sun's gravitational influence, it began to experience conditions it hadn't encountered since leaving its birth system eons ago. Solar radiation, initially faint but steadily increasing, began to warm its surface and drive the sublimation processes that would make it visible to our telescopes. The trajectory of 3I Atlas as it approached our solar system provides clues about its galactic origins. By tracing its orbit backward through space and accounting for the motion of our solar system through the galaxy, astronomers can estimate the general direction from which it came. This information, while imprecise due to gravitational perturbations over vast timescales, helps constrain the possible stellar systems that might have been its original home. The speed of 3I Atlas relative to our solar system also provides information about its journey. Objects that have traveled for very long periods tend to have velocities that reflect the average motion of stars in their region of the galaxy, while those ejected more recently might retain velocity components related to their original stellar system's motion. The observed velocity of 3I Atlas suggests a journey of considerable duration through interstellar space. As 3I Atlas entered our solar system's sphere of influence, it began to interact with the solar wind, the stream of charged particles flowing outward from our sun. This interaction would have been the first taste of stellar activity the object had experienced in millions of years, beginning the process of awakening that would eventually make it visible to our telescopes and reveal its mysterious nature to human observers. The long journey of 3I Atlas through interstellar space represents one of the most extreme odysseys possible for any object in the universe. Having survived the transition from a comfortable orbit around its birth star to the harsh environment of the galactic void, it carries within its structure and composition a record of processes and conditions that exists nowhere else. Its arrival in our solar system provides us with a unique opportunity to study materials and phenomena that have been shaped by the cosmos on its grandest scale. As the weeks passed and Hubble continued its patient observations of 3I Atlas, astronomers began to realize that they were witnessing something unprecedented in the study of interstellar visitors. The telescope's exquisite resolution and sensitivity were revealing details about this cosmic wanderer that challenged every assumption about what interstellar objects should look like and how they should behave. In the quiet darkness of space, 3I Atlas was telling a story that no one had expected to hear. The most startling discovery came when Hubble's images began to show clear evidence that 3I Atlas was not a single intact object, but rather a collection of fragments traveling together through space. What had appeared as a unified comet in ground-based observations resolved into multiple distinct brightness peaks when viewed with Hubble's superior resolution. The implications were staggering. Astronomers were witnessing the real-time disintegration of an interstellar visitor. The fragmentation pattern revealed by Hubble was unlike anything previously observed in solar system comets. Instead of the catastrophic breakup events that sometimes occur when comets approach too close to the Sun, 31ATLAs appeared to be undergoing a more gradual dissolution. Individual fragments became visible as discrete sources of light within. The overall coma is following slightly different trajectories as they continued their journey through our solar system. Hubble's time series observations captured the evolution of this fragmentation process with unprecedented detail. Images taken days or weeks apart showed how individual fragments brightened and faded, how new fragments appeared while others disappeared, and how the overall structure of the fragment swarm evolved over time. It was like watching a slow motion. Explosions spread across millions of kilometers of space. The size distribution of the fragments provided crucial insights into the breakup mechanism. Hubble's photometry revealed that most of the visible fragments were quite small, probably only a few meters to tens of meters across. This size range suggested that the original object had been relatively fragile. It's held together by weak forces that were easily overcome by the stresses of its journey through interstellar space, or its encounter with our solar system's environment, even. More surprising was the discovery that different fragments showed different levels of activity. While some fragments displayed bright, well-developed comet indicative of active sublimation, others appeared relatively inactive despite being composed of presumably similar materials. This variation suggested that the fragmentation had exposed different types of material, or that the individual pieces were experiencing different thermal or mechanical stresses. Hubble's spectroscopic capabilities allowed astronomers to study the composition of the gas and dust being released by the fragmenting object. The spectra revealed the presence of water vapor, carbon monoxide, and other typical cometary gases, but in proportions that differed subtly from solar system comets. More intriguingly, some spectral features suggested the presence of more exotic ices or organic compounds that might have formed during the object's long journey through interstellar space. The dust properties revealed by Hubble's observations were equally fascinating. Polarimetric measurements suggested that the dust grains being released by 3I Atlas had unusual optical properties, possibly indicating different mineral compositions or grain sizes than typically found in solar system dust. The dust appeared to be unusually fluffy and porous, consistent with materials that had been modified by prolonged exposure to the harsh environment of interstellar space. Hubble's thermal infrared observations provided additional surprises about the temperature and thermal properties of 3I-ATLAS. The fragments appeared to be heating up and cooling down in ways that didn't match simple models of solar heating and thermal emission. This behavior suggested either unusual thermal properties of the surface materials or complex internal structures that affected heat transfer within the fragmenting object. The orbital dynamics of the individual fragments, measured by Hubble's precise astrometry, revealed subtle differences in their trajectories. While all fragments were following hyperbolic paths that would eventually carry them out of the solar system, small variations in their velocities and directions indicated that the fragmentation process had imparted different impulses to different pieces. This information provided clues about the mechanism responsible for the breakup. Perhaps most remarkably, Hubble detected what appeared to be ongoing fragmentation events during the observation period. New fragments seemed to appear in real time, suggesting that the disintegration of 3I Atlas is an active process rather than the result of a single catastrophic event in the past. This ongoing breakup provided astronomers with a rare opportunity to study the internal structure and composition of an interstellar object as it revealed its secrets layer by layer. The mass loss rate from 3I-ATLAS, calculated from Hubble's measurements of gas and dust production, was surprisingly high for such a small object. The rate at which material was being lost suggested that the fragmentation process was quite efficient at exposing fresh ices to solar radiation. If this rate continued, the entire object would disappear within a relatively short time, leaving only a dispersed cloud of dust and gas as evidence of its passage through our solar system. Hubble's observations also revealed unexpected asymmetries in the dust and gas distribution around 3I-ATLAS. Instead of the roughly symmetric coma typical of solar system comets, the interstellar visitor showed complex structures with jets, fans, and other directional features that suggested non-uniform outgassing from its fragmenting surface. These asymmetries provided information about the rotation state and internal structure of the disintegrating object. The discovery of fragmentation in 3I Atlas raised profound questions about the structural integrity of interstellar objects in general. If this visitor could break apart under the relatively mild stresses of approaching our Sun, what did this imply about the survival prospects of other interstellar travelers? How many objects might fragment so completely during their passage through solar systems that they become undetectable, leaving no trace of their visit? Hubble's unprecedented observations of 3I Atlas provided the first detailed look at how an interstellar visitor responds to the environment of our solar system. The fragmentation process revealed that these cosmic wanderers might be far more fragile than previously assumed. Held together by weak forces that can be disrupted by thermal stresses, tidal forces, or rotational instabilities. This discovery added a new dimension to the study of interstellar objects and highlighted the importance of rapid, intensive observation campaigns for future visitors. The case of 3I Atlas demonstrated the unique value of space-based observations for studying these mysterious objects. Only Hubble's combination of high resolution, stability, and multi-wavelength capabilities made it possible to detect and monitor the fragmentation process in such detail. The discovery emphasized how much still remains to be learned about interstellar visitors and the processes that shape them during their long journeys through the galaxy. To truly understand the mysteries revealed by 3I Atlas, we must turn our gentle attention to the vast realm through which it has traveled, the interstellar medium, that tenuous ocean of gas, dust, and energy that fills the spaces between stars. Far from being empty vacuum, interstellar space is a complex and dynamic environment that shapes and modifies any object brave enough to venture into its depths for extended periods. The interstellar medium exists in a state of constant, gentle motion, stirred by stellar winds, supernova explosions, and the gravitational dance of stars within the galaxy. Its density varies dramatically from place to place, from the sparse hydrogen gas that fills most of the galactic volume to the dense molecular clouds where new stars are born. An object like 3I Atlas, traveling through this medium for millions of years, would encounter this full spectrum of interstellar conditions. The temperature of interstellar space presents one of its most challenging aspects for wandering objects. Away from the warming influence of nearby stars, temperatures can drop to just a few degrees above absolute zero. At these extreme temperatures, materials become brittle and prone to fracturing. Thermal cycling, as an object moves between regions of different temperature, can create repeated stress cycles that gradually weaken structural bonds and make fragmentation more likely. Cosmic radiation permeates interstellar space, creating a harsh environment for any object exposed to its effects over geological timescales. High-energy particles from distant sources bombard interstellar travelers, gradually breaking down organic molecules and altering surface chemistry. This process, known as space weathering, can fundamentally change the optical and thermal properties of an object's surface, creating dark, radiation-processed layers that mask the original composition beneath. The magnetic fields that thread through interstellar space create complex patterns of charged particle flow that can affect objects traveling through the medium. While these fields are generally weak compared to planetary magnetic fields, over the vast distances and long timescales involved in interstellar travel, they can influence the radiation environment experienced by wandering objects and potentially affect their structural evolution. Dust grains in the interstellar medium, though sparse by terrestrial standards, can have cumulative effects on objects traveling at high velocities over long periods. Each microscopic impact contributes to surface erosion and can gradually remove material from the outer layers of interstellar travelers. This process might expose subsurface materials with different properties, contributing to the unusual characteristics observed in objects like 3I Atlas. The chemical environment of interstellar space is both sparse and diverse. While hydrogen is by far the most abundant element. The medium also contains traces of heavier elements and complex molecules, including organic compounds formed through gas phase chemistry or on the surfaces of dust grains. Objects traveling through this environment for extended periods might accumulate these materials or undergo chemical reactions that alter their surface composition. The pressure environment of interstellar
space
is virtually non-existent by terrestrial standards. Yet this near-perfect vacuum can have significant effects on the structural integrity of objects over long timescales. Materials that might be stable in the higher pressure environment of a solar system can become unstable in the extreme vacuum of interstellar space, leading to sublimation, outgassing, or structural changes that weaken the overall integrity of wandering objects. Gravitational interactions in interstellar space occur on scales and timescales that dwarf anything experienced within a solar system. While individual interactions with passing stars are rare, they can be dramatic when they occur, potentially altering the trajectory of interstellar travelers, or subjecting them to tidal forces that could trigger fragmentation or structural changes. The cumulative effect of many small gravitational perturbations over millions of years can also gradually modify an object's rotation state and internal stress distribution. The passage through different phases of the interstellar medium exposes wandering objects to varying conditions that can have cumulative effects on their structure and composition. Dense molecular clouds provide temporary shielding from cosmic radiation, but expose objects to different chemical environments and potentially higher dust densities. The hot, low-density gas found in superbubbles created by stellar winds and supernova presents yet another environment with its own unique challenges for structural integrity. The formation and evolution of the galaxy itself create large-scale flows in density, variations in the interstellar medium that can affect the paths and experiences of objects traveling between stars. Spiral density waves, galactic winds driven by star formation activity, and the overall rotation of the galaxy create patterns of motion and density that interstellar travelers must navigate during their long journeys. The timescales involved in interstellar travel are almost incomprehensible from a human perspective. An object like 3I Atlas might have spent millions or even billions of years in the interstellar medium, during which the galaxy itself has evolved and changed. Stars have been born and died, new elements have been created and dispersed, and the chemical composition of the interstellar medium has gradually evolved, all while our visitor has continued its lonely journey through the cosmic void. The encounter with molecular clouds during interstellar travel can be particularly significant for the evolution of wandering objects. These dense regions of gas and dust can provide temporary refuge from cosmic radiation while subjecting travelers to different physical and chemical conditions. The passage through a molecular cloud might trigger chemical reactions on an object's surface, deposit new materials, or create thermal gradients that contribute to structural stress and eventual fragmentation. The isolation experienced by interstellar travelers is perhaps their most defining characteristic. Far from any star, these objects exist in conditions of extreme cold, darkness, and solitude that no object within a solar system ever experiences. This isolation allows processes to operate that would be overwhelmed by stellar activity in a normal planetary environment, potentially creating unique materials or structures that can only form in the depths of interstellar space. Understanding the nature of interstellar space helps explain many of the unusual characteristics observed in objects like 31ATLAS. The fragmentation observed by Hubble might be the delayed result of structural weakening that occurred over millions of years of exposure to the harsh interstellar environment. The unusual composition and behavior of interstellar visitors might reflect the cumulative effects of processes that operate only in the unique conditions found between the stars. The study of interstellar visitors, like 3I Atlas, provides our only direct way to learn about conditions and processes in the interstellar medium. These objects serve as natural probes that have sampled vast regions of space over enormous timescales, carrying with them physical and chemical records of their experiences. By studying their properties and behavior, astronomers can gain insights into the nature of interstellar space and that would be impossible to obtain through remote observations alone. The discoveries made about 3I Atlas through Hubble's detailed observations have profound implications that extend far beyond the understanding of a single interstellar visitor. In the gentle way that scientific discoveries ripple outward to touch many areas of knowledge, the fragmentation and unusual behavior of this cosmic wanderer are forcing astronomers to reconsider fundamental assumptions about planetary formation, stellar system evolution, and the nature of the galaxy itself. The fragmentation of 3I Atlas suggests that many interstellar objects might be far more fragile than previously assumed. This has immediate implications for models of how these objects survive their ejection from home stellar systems and their subsequent journeys through interstellar space. If objects commonly fragment during these processes, then the population of interstellar travelers might be dominated by debris and fragments rather than intact primordial bodies. This fragility also affects estimates of the total population of interstellar objects in the galaxy. If many visitors fragment so completely during their passage through solar systems that they become undetectable, then surveys based on successful detections might be dramatically underestimating the true number of interstellar travelers. Galaxy might be filled with far more wandering objects than current observations suggest. Most of them too small or dispersed to be easily detected. The implications for planetary formation theory are equally significant. The existence of fragile objects like 3I Atlas suggests that not all small bodies in stellar systems undergo the collisional processing and gravitational stirring that creates the robust asteroids and comets we see in our own solar system. Some objects might retain their primordial, loosely bound structure throughout their time in their home system, only revealing their fragility when subjected to the stresses of interstellar travel or encounters with foreign stellar environments. Unusual composition and behavior of 3I Atlas also have implications for our understanding of the chemical evolution of the galaxy. If interstellar travelers carry chemically processed materials from one stellar system to another, they might serve as a mechanism for distributing elements and compounds throughout the galaxy. The fragmentation observed in 3I Atlas could make this distribution process even more efficient by creating larger surface areas for chemical interaction with the interstellar medium. For astrobiology, the discovery of fragmentation in interstellar visitors raises both challenges and opportunities. On one hand, the structural instability suggested by 3I Atlas's behavior might make it difficult for these objects to transport delicate organic molecules or microbial life between stellar systems. On the other hand, fragmentation could expose protected internal materials to space, potentially preserving some biological signatures while destroying others. The timing and mechanism of fragmentation in 3I Atlas provide insights into the relative importance of different stress sources for interstellar objects. The fact that fragmentation appears to have occurred as the object approached our solar system suggests that thermal stresses from solar heating might be more important than previously thought for triggering the breakup of these visitors. This has implications for predicting which interstellar objects will remain intact and which will fragment during their passage through solar systems. The observations of 3I Atlas also contribute to our understanding of how stellar systems exchange material with the galaxy. The fragmentation process observed by Hubble shows how objects from other systems might distribute their material throughout our solar system, potentially contributing to the chemical inventory of our own interplanetary environment. Over geological timescales, this process might have significant cumulative effects on the composition of planetary atmospheres and surfaces. The theoretical models used to predict the behavior of interstellar objects must now account for the possibility of fragmentation. And the complex thermal and mechanical processes that 3I Atlas has revealed, simple models that treat these visitors as monolithic bodies clearly need to be updated to include the effects of internal structure, material strength, and the various stress sources that can trigger breakup during interstellar travel or solar system encounters. The discovery of ongoing fragmentation in 3I Atlas also has implications for the interpretation of observations of other interstellar visitors. The unusual characteristics of Oumuamua, for instance, might be better understood. if that object was also undergoing fragmentation or had recently experienced a breakup event. This possibility requires re-examination of existing data and suggests that fragmentation might be a common feature of interstellar visitors rather than an exceptional occurrence. For galactic dynamics, the existence of fragile interstellar travelers like 3I Atlas provides new constraints on models of how objects move between stellar systems. The efficiency of material exchange between systems depends not only on ejection, its mechanisms, but also on the survival probability of ejected objects during their interstellar journeys. If fragmentation is common, then the galaxy-wide redistribution of materials might occur through different pathways than previously. Envision the implications extend to our understanding of the early solar system and its formation. If our own system was visited by interstellar objects during its formation period, and if these visitors commonly fragmented as they approached the young sun, then they might have contributed more material to the developing planetary system than would be expected from intact objects alone. This could affect models of early planetary accretion and atmospheric evolution. The study of 3I Atlas also highlights the importance of rapid response capabilities for future interstellar visitor discoveries. Because these objects may undergo dramatic changes or complete disintegration during their passage through solar systems, astronomers need to be prepared to conduct intensive observation campaigns immediately after discovery. The development of automated detection and alert systems becomes even more crucial. When the targets of study might literally disappear during the observation period, the theoretical framework for understanding interstellar objects must also account for the possibility that different classes of visitors might exist, each with characteristic behaviors and survival probabilities. Objects like 3I Atlas might represent a population of fragile, loosely bound bodies that fragment readily, while others like 2I Borisov might represent more robust objects that can survive interstellar travel intact. Understanding these different populations will require statistical studies of many more interstellar visitors than have been discovered to date. Perhaps most profoundly, the case of 3I ATLAs demonstrates that the universe continues to surprise us with phenomena that challenge our theoretical understanding. In the gentle humility that comes with scientific discovery, astronomers are learning that their models of interstellar objects, while based on sound physical principles, may have been too simplistic to capture the full complexity of these cosmic wanderers. Each new discovery expands the catalog of possibilities and requires theorists to develop more sophisticated models that can account for the rich diversity of behaviors observed in nature. The theoretical implications of 3I ATLAS will likely continue to unfold as astronomers analyze its observations more deeply and as new interstellar visitors are discovered and studied. The gentle revolution in understanding that this single object has triggered demonstrates how individual discoveries can have far-reaching consequences for multiple areas of astronomical research, connecting the study of small bodies to the grand questions of galactic evolution and the cosmic distribution of matter and life. The study of interstellar visitors like 3I ATLAS presents some of the most demanding observational challenges in modern astronomy. These objects appear briefly in our cosmic neighborhood, often faint and distant, moving against the background of stars with trajectories that carry them quickly back into the darkness of space. The window of opportunity for detailed study is narrow, requiring astronomers to marshal their most sophisticated instruments and techniques in a race against time and celestial mechanics. The initial detection of interstellar visitors relies on automated sky surveys that scan vast areas of the sky each night, looking for moving objects against the fixed pattern of background stars. These surveys, designed primarily to detect potentially hazardous asteroids and comets, must process enormous amounts of data quickly to identify candidates for follow-up observation. The software algorithms that flag potential interstellar visitors must be sensitive enough to detect faint objects while avoiding false alarms from cosmic ray hits, detector artifacts, and other spurious signals. Once a potential interstellar visitor has been identified, the challenge shifts to rapid confirmation and characterization. The object's motion must be tracked precisely over several nights or weeks to determine its orbital elements and confirm its interstellar nature. This requires coordinated observations from multiple observatories, often spanning several continents to ensure continuous coverage as Earth rotates. The calculations involved in orbit determination must account for gravitational perturbations from all the major planets and the effects of solar, radiation pressure on the object's trajectory. The faintness of interstellar visitors presents perhaps the greatest challenge for detailed study. Objects like 3I Atlas are often barely detectable, even with the world's largest telescopes, requiring long exposure times to accumulate enough light for meaningful analysis. The need for long exposures conflicts with the object's motion across the sky, necessitating sophisticated tracking techniques that can follow the target's movement while keeping background stars sharp for reference. Spectroscopic analysis of interstellar visitors requires even more light than simple imaging, making compositional studies extremely challenging. The weak signals must be extracted from instrumental noise and contamination from Earth's atmosphere, requiring careful calibration and data reduction techniques. Space-based telescopes like Hubble have advantages in this regard, but even they are limited by the fundamental challenge of collecting enough photons from such distant, faint targets. The rapid motion of interstellar visitors creates additional complications for observation scheduling and data analysis. Ground-based telescopes must constantly adjust their pointing to track the moving target, while space-based observatories face constraints on their ability to observe objects in certain parts of the sky or during certain times of year. The timing of observations becomes critical, as opportunities to study these objects at their closest approach to Earth may last only days or weeks. Atmospheric effects pose significant challenges for ground-based observations of interstellar visitors. Earth's atmosphere absorbs certain wavelengths of light and introduces distortions that blur images and reduce sensitivity. Adaptive optics systems can partially compensate for atmospheric turbulence, but they work best on bright objects and may not be fully effective for the faint targets that interstellar visitors typically present. Weather conditions at observatory sites can become critical factors that can make or break important observation campaigns. The interpretation of observations is complicated by the unknown nature of interstellar objects and their potentially exotic properties. Standard models developed for solar system comets and asteroids may not apply to objects that have spent millions of years in the harsh environment of interstellar space. Astronomers must be careful not to force observations into preconceived frameworks while remaining rigorous about distinguishing real signals from instrumental artifacts or analysis errors. Coordinating observations of interstellar visitors across multiple observatories and wavelength ranges requires unprecedented levels of international cooperation and rapid communication. When 3I Atlas was discovered, astronomers around the world needed to quickly redirect their telescopes and observation programs to study this unexpected visitor. Logistics of scheduling observations on oversubscribed facilities while maintaining ongoing research programs present significant challenges for the astronomical community. The analysis of data from interstellar visitors often requires development of new techniques and software tools. Standard astronomical analysis packages may not include routines for handling the unique characteristics of these objects, necessitating custom software development under tight time constraints. The combination of faint signals, complex instrumental effects, and unusual target properties pushes data analysis techniques to their limits and beyond. Publication and peer review of results from interstellar visitor studies face their own challenges. The urgency of documenting observations before objects fade from view conflicts with the normally deliberate pace of scientific publication. Astronomers must balance the need for rapid dissemination of results with the requirement for thorough analysis and peer review that ensures scientific quality. The unique nature of these observations often means that results cannot be independently verified by other researchers observing the same object. The development of specialized instruments and techniques for studying interstellar visitors is an ongoing challenge for the astronomical community. Future surveys like the Vera Rubin Observatory will detect many more interstellar objects, but they will also demand rapid response capabilities from follow-up facilities. The design and construction of instruments optimized for faint, moving targets requires years of advanced planning and significant financial investment. Modeling the behavior of interstellar visitors presents unique theoretical challenges. The complex interplay of thermal effects, structural properties, and outgassing processes observed in objects like 3I Atlas requires sophisticated numerical models that push the boundaries of computational capabilities. These models must account for processes operating over vastly different timescales. From the microsecond dynamics of molecular sublimation to the million-year evolution of objects in interstellar space, the statistical study of interstellar visitor populations requires accumulating observations of many objects over extended periods. With only a few confirmed detections to date, astronomers are working with extremely small sample sizes that make it difficult to identify patterns or draw general conclusions. Building up statistically meaningful samples will require decades of systematic observation and may reveal that early discoveries were not representative of the broader population. Perhaps the greatest challenge in studying interstellar visitors is the fundamental unpredictability of these encounters. Each new discovery brings unexpected characteristics and behaviors that challenge existing theoretical frameworks and observational techniques. The case of 3I Atlas, with its surprising fragmentation revealed by Hubble observations, demonstrates that even carefully planned observation campaigns may uncover phenomena that no one anticipated. This unpredictability makes it difficult to prepare optimal observation strategies and may require astronomers to remain flexible and adaptive in their approaches. Despite these formidable challenges, the study of interstellar visitors represents one of the most exciting frontiers in modern astronomy. Each successful observation campaign adds valuable data to our understanding of these cosmic wanderers and the galaxy-wide processes that create and shape them. Involved in these studies drive innovation in astronomical instrumentation and analysis techniques, benefiting the broader field of astronomy. As technology continues to advance and more interstellar visitors are discovered, astronomers are developing the tools and techniques needed to unlock the secrets these cosmic messengers carry from the depths of space, with 3 confirmed interstellar visitors now cataloged by astronomers. The opportunity arises for comparative analysis that can reveal patterns and differences among these cosmic wanderers. Each object, Oumuamua, 2I Borisov, and 3I Atlas, tells its own unique story of interstellar travel and stellar system encounters. Yet together, they begin to paint a picture of the diverse population of objects that drift between the stars. Throughout our galaxy, Oumuamua, the first confirmed interstellar visitor, established the baseline for what such objects might look like and how they might behave. Its highly elongated shape, unusual reflectivity, and lack of detectable outgassing marked it as distinctly different from familiar solar system objects. The non-gravitational acceleration it exhibited as it left our solar system sparked debates about its composition and structure that continue to this day. Oumuamua's behavior suggested that interstellar visitors might be fundamentally different from the asteroids and comets that populate our own stellar neighborhood. In stark contrast, 2I Borisov appeared comfortingly familiar to astronomers accustomed to studying solar system comets, displayed clear signs of outgassing, developed a well-formed coma and tail, and behaved much as theory predicted an icy body should when approaching the sun. Spectroscopic observations revealed water vapor and other gases typical of cometary compositions, suggesting that at least some interstellar visitors are quite similar to objects formed in our own solar system. Borisov's familiarity provided reassurance that the processes governing comet formation and evolution might be universal throughout the galaxy. 3I Atlas occupies a middle ground between the enigmatic nature of Oumuamua and the familiar behavior of Borisov. Like Borisov, it shows clear signs of cometary activity without gassing and coma formation. Yet its fragmentation behavior and unusual characteristics set it apart from typical solar system comets. The discovery that 3I Atlas was breaking apart during its passage through our solar system added a new dimension to the catalog of possible behaviors for interstellar visitors. The size estimates for these 3 objects span a considerable range. Though all are relatively small by astronomical standards, Oumuamua was estimated to be several hundred meters in its longest dimension, with its highly elongated shape making precise size determination challenging. Borisov appeared to be somewhat smaller, with a nucleus perhaps a few kilometers across typical. For solar system comets, the individual fragments of 3I-ATLAs appear to be much smaller still, suggesting that the original object was also quite modest in size, or that the fragmentation process has created numerous small pieces from a larger parent body. The compositional differences among the three visitors provide insights into the diversity of materials that exist in interstellar space and other stellar systems. Oumuamua's composition remains mysterious, with various theories proposing everything from a shard of solid nitrogen to a fragment of a disrupted planet. Borisov's composition appeared similar to solar system comets, with water ice and typical volatile compounds. 3I-ATLAS shows evidence of water and other familiar compounds, but with proportions and behaviors that suggest either different formation conditions or modification during its interstellar journey. The orbital characteristics of the three visitors also reveal important differences in their origins and trajectories. Oumuamua approached from the direction of the constellation Lyra, with a moderately hyperbolic orbit that carried it quickly through our solar system. Borisov arrived from a different direction with its own distinct trajectory. 3I-ATLAs followed yet another path, suggesting that interstellar visitors arrive from various directions as might be expected from a distributed galactic population rather than from any specific source region. The activity levels and evolution patterns of the three objects during their solar system encounters provide crucial data for understanding how interstellar travelers respond to stellar environments. Oumuamua showed no detectable outgassing, yet somehow experienced non-gravitational acceleration. Borisov displayed steady, predictable activity consistent with solar heating of surface ices. 3I-ATLAS showed variable and ultimately catastrophic activity that led to fragmentation, suggesting that structural integrity can play a crucial role in determining an object's survival during its solar encounter. The discovery circumstances of each visitor highlight the improving capabilities of astronomical surveys and the somewhat serendipitous nature of these detections. Oumuamua was discovered by Pan-STARRS during its routine asteroid survey, but only after it had already passed closest approach to the Sun and was heading outward. Borisov was found by an amateur astronomer, demonstrating that important discoveries can still be made with modest equipment by dedicated observers. 3I-ATLAS was detected by the ATLAS survey system, showing how automated sky monitoring continues to expand our ability to find these rare visitors. The observational challenges presented by each object varied significantly based on their properties and the timing of their discovery. Oumuamua was already quite faint when discovered, and became increasingly difficult to observe as it receded from the Sun. Borisov was discovered earlier in its approach, allowing for months of detailed study. As it reached perihelion, 3I-ATLAS provided yet another observational scenario, with its fragmentation creating new challenges and opportunities for understanding interstellar object structure and evolution. The theoretical implications drawn from each visitor have evolved. As the sample size has grown, Oumuamua's unusual properties led to exotic theories about its nature and origin. Borisov's familiarity suggested that interstellar objects might be quite similar to solar system bodies. 3I-ATLAS has now introduced the concept that structural fragility might be an important characteristic of some interstellar travelers. Adding another layer of complexity to theoretical models, the media and public attention received by each discovery also reflects the evolving understanding of interstellar visitors. Oumuamua generated enormous interest, partly due to its unusual properties and the exotic explanations proposed for its behavior. Borisov received less sensational coverage, but provided steady scientific interest as a more normal interstellar comet. 3I-ATLAS, with its fragmentation drama revealed through Hubble observations, has captured attention for demonstrating the dynamic and sometimes violent processes that can affect these cosmic wanderers. The follow-up observation campaigns for each visitor have demonstrated the importance of rapid response and international cooperation in maximizing scientific return. Each object has pushed observational capabilities in different ways and has driven improvements in survey techniques, observation planning, and data analysis methods. The lessons learned from studying each visitor have informed strategies for observing future interstellar objects. Perhaps most significantly, the comparative analysis of these 3 visitors reveals that interstellar objects are likely to be far more diverse than initially expected. Rather than representing a single class of cosmic wanderer, they appear to encompass a range of sizes, compositions, structures, and behaviors that reflects the complexity of planetary formation and evolution processes throughout the galaxy. This diversity suggests that many more discoveries will be needed to fully understand the population of interstellar travelers and their implications for galactic astronomy and astrobiology. The emergence of patterns and differences among interstellar visitors also provides guidance for future observation strategies and theoretical modeling efforts. Understanding which characteristics are common and which are exceptional helps astronomers prepare for future discoveries and develop more sophisticated models of interstellar object populations. Each new visitor adds to this growing understanding, while likely introducing new surprises that will continue to challenge and expand our knowledge of these remarkable cosmic messengers. The mysteries revealed by 3I Atlas and its unexpected fragmentation have launched an intensive scientific investigation that extends far beyond the observation of this single object. Astronomers around the world are now engaged in a careful analysis of all available data, developing new theoretical models, and preparing for future discoveries that might help answer the profound questions raised by this enigmatic visitor from interstellar space. The detailed analysis of Hubble's observations of 3I Atlas requires sophisticated techniques to extract maximum information from every precious photon captured by the telescope. Astronomers are employing advanced image processing methods to track individual fragments as they separate and evolve, measuring their brightness variations, colors, and motions with unprecedented precision. Each frame of data represents a snapshot of an ongoing process that may never be observed again, making every measurement valuable for understanding the fragmentation mechanism and its implications. Spectroscopic analysis of the gas and dust released by 3I Atlas is providing crucial insights into the object's composition and the processes driving its disintegration. Researchers are carefully measuring the ratios of different molecular species, looking for signatures of exotic ices or organic compounds that might have formed during the object's interstellar journey. The temporal evolution of the spectrum as fragmentation proceeds offers clues about the internal structure and composition gradients within the original object. Theoretical modeling efforts are working to understand the physical processes that could lead to the observed fragmentation pattern. Computer simulations are exploring various scenarios, from thermal stress cracking due to solar heating to rotational breakup caused by outgassing torques. These models must account for the unique properties of materials that have been modified by millions of years of exposure to the interstellar environment, including radiation processing and micrometeorite bombardment. International collaboration has become essential for maximizing the scientific return from observations of 3I Atlas and other interstellar visitors. Research teams from institutions around the world are sharing data, expertise, and computational resources to tackle questions that no single group could address alone. This collaborative approach reflects the global nature of modern astronomy and the recognition that interstellar visitors represent opportunities that benefit the entire scientific community. Laboratory experiments are being designed to test hypotheses about the behavior of materials under conditions similar to those experienced by interstellar objects. Researchers are subjecting ice mixtures to radiation doses and temperature cycles that simulate interstellar exposure, then studying how these materials respond to rapid heating that mimics solar system encounters. These experiments provide crucial constraints for theoretical models and help distinguish between different proposed mechanisms for the observed behaviors. Archive. Searches are being conducted to look for evidence of similar fragmentation events in past observations that might have been overlooked or misinterpreted. Astronomers are re-examining data from previous comet observations to see whether other objects have shown similar patterns of behavior that were not recognized at the time. These retrospective studies might reveal that fragmentation is more common than previously thought. Both among interstellar visitors and solar system objects, survey programs are being enhanced to improve the detection and early characterization of future interstellar visitors. The lessons learned from 3I-ATLAS about the importance of rapid, intensive follow-up observations are driving improvements in automated alert systems and rapid response protocols. New algorithms are being developed to identify potential fragmentation events in real time, allowing astronomers to mobilize resources quickly when similar phenomena are detected. The upcoming Vera Rubin Observatory, with its unprecedented survey capabilities, promises to revolutionize the field of interstellar object research. This facility will detect interstellar visitors at much greater distances and earlier in their approach to the solar system, providing extended observation windows. For detailed study, the observatory's ability to track thousands of objects simultaneously will enable statistical studies of interstellar object populations that are impossible with current facilities. Space-based missions are being proposed specifically to study interstellar visitors in detail. Concepts include rapid-response spacecraft that could be launched to rendezvous with newly discovered objects, providing close-up observations and even sample return capabilities. While technically challenging due to the high velocities and unpredictable timing of interstellar encounters, such missions could provide unprecedented insights into the nature and origin of these cosmic wanderers. Computational resources are being marshaled to conduct large-scale simulations of interstellar object populations and their evolution. These studies aim to predict the observable characteristics of different types of interstellar travelers and help interpret the growing catalog of discoveries. The simulations must account for complex processes operating over galactic scales and geological timescales, pushing the boundaries of current computational capabilities. The search for answers about 31ATLAS is also driving advances in instrumentation and observational techniques. New detector technologies are being developed to improve sensitivity for faint, rapidly moving targets. Adaptive optic systems are being optimized for tracking moving objects. New spectroscopic techniques are being developed to extract compositional information from weak signals contaminated by terrestrial atmospheric effects. Data sharing initiatives are being established to ensure that observations of interstellar visitors are preserved, made available to the global research community. Given the unrepeatable nature of these observations, it is crucial that data be properly archived and documented for future analysis as new techniques and theoretical understanding develop. These efforts include the development of standardized data formats and metadata standards for interstellar object observations. Educational and outreach efforts are communicating the excitement and importance of interstellar visitor research to the next generation of astronomers and the general public. The dramatic story of objects like 3I-ATLAS traveling for millions of years between stars before fragmenting in our solar system captures the imagination and helps explain fundamental concepts about planetary formation, stellar evolution, and galactic dynamics. The search for answers continues to reveal new questions as each analysis of 3I-ATLAS data uncovers additional complexities and unexpected behaviors. This is the nature of frontier science, where each answer opens new avenues of investigation and each discovery challenges existing theoretical frameworks. The case of 3I-ATLAS demonstrates that the universe continues to surprise us with phenomena that expand our understanding of cosmic processes and the rich diversity of objects that populate our galaxy, as the scientific investigation of 3I-ATLAS continues. Researchers maintain the patient, methodical approach that characterizes the best scientific research. While the excitement of discovery drives rapid initial analysis, the deeper understanding that emerges from careful, thorough investigation takes time to develop. The answers being sought about this remarkable interstellar visitor will likely emerge gradually as multiple lines of evidence converge to paint a coherent picture of its nature, origin, and the processes that shaped its dramatic encounter with our solar system. The discovery and detailed study of interstellar visitors like 3I Atlas carries profound implications for astrobiology, the interdisciplinary field that seeks to understand the origin, evolution, distribution, and future of life in the universe. These cosmic wanderers represent potential vectors for transporting organic compounds and perhaps even microbial life between stellar systems, a process known as panspermia that could fundamentally alter our understanding of how life spreads. Throughout the galaxy, the fragmentation observed in 3I Atlas adds new complexity to discussions of panspermia and interstellar transport of biological materials. On one hand, the breakup of the object exposes internal materials that have been shielded from the harsh radiation environment of interstellar space, potentially preserving delicate organic molecules or even dormant microorganisms. On the other hand, fragmentation also exposes these materials to solar radiation and the vacuum of space, conditions that are generally hostile to biological preservation. The composition of interstellar visitors provides crucial evidence about the chemical inventory available for life in other stellar systems. Spectroscopic observations of 3I Atlas and other interstellar objects reveal the presence of water, carbon compounds, and other molecules essential for life as we know it. The similarity of these compositions to solar system objects suggests that the basic chemical building blocks of life are widely distributed throughout the galaxy, supporting the possibility that life could arise independently in many different stellar environments. The survival of organic compounds during interstellar travel presents both challenges and opportunities for biological transport. The harsh conditions of interstellar space, extreme cold, vacuum, and radiation are generally hostile to complex organic molecules and living organisms. However, the interiors of objects like 3I Atlas might provide some protection from these conditions, potentially allowing organic materials to survive for the millions of years required for interstellar travel. Laboratory studies of extremophile microorganisms have demonstrated that some forms of life can survive conditions similar to those found in space for extended periods. Experiments aboard the International Space Station and other platforms have shown that certain bacteria and archaea can remain viable after exposure to vacuum, radiation, and temperature extremes. These findings suggest that at least some forms of life might be hardy enough to survive interstellar transport. Though the timescales involved in such journeys remain challenging, the frequency of interstellar visitors in our solar system provides constraints on the efficiency of biological transport between stellar systems. Current estimates suggest that dozens of interstellar objects pass through the inner solar system each year, most too small or faint to detect with current technology. If even a small fraction of these visitors carry viable microorganisms, the cumulative effect over geological timescales could be significant for seeding life on suitable worlds. The impact, or close, approach of interstellar visitors to planets could provide mechanisms for transferring biological materials from these objects to planetary surfaces. While most interstellar objects follow trajectories that carry them quickly out of solar systems, gravitational interactions with planets could occasionally result in impacts or atmospheric encounters that deposit material from interstellar space onto planetary surfaces. Such events might have played a role in delivering organic compounds or microorganisms too early. Earth or other potentially habitable worlds. The study of 3I Atlas and its fragmentation also raises questions about the detectability of biological signatures in interstellar objects. Current observational techniques are barely capable of determining basic compositional information about these faint, distant targets. Detecting complex organic molecules or biosignatures would require even more sensitive instruments and longer observation times than are currently available. Future space-based missions might be needed to provide the detailed analysis necessary to search for evidence of life in interstellar visitors. The origins of interstellar objects and other stellar systems provide insights into the conditions and processes that might support life elsewhere in the galaxy. Objects ejected from the outer regions of stellar systems, where temperatures are low and organic compounds can remain stable, might carry samples of prebiotic chemistry or even biological materials from their home environments. Studying these Objects could provide our first direct samples of materials from potentially habitable worlds around other stars. The implications of interstellar transport extend to our understanding of the origin of life on Earth. If microorganisms or organic precursors to life can travel between stellar systems, then life on Earth might not represent an independent origin, but rather one link in a galactic web of biological connectivity. This possibility would fundamentally alter our estimates of the probability of life arising in the universe and the likelihood of finding life elsewhere. The diversity observed among interstellar visitors suggests that they sample a wide range of environments and conditions from throughout the galaxy. This diversity increases the likelihood that at least some visitors might carry biological materials or organic compounds formed under conditions very different from those in our solar system. Studying this diversity could provide insights into alternative biochemistries and the range of conditions under which life might arise and persist. The timescales involved in interstellar travel also have important implications for biological transport. Objects like 3I Atlas have likely traveled for millions or billions of years between stellar systems, far longer than any known organism can remain viable without active metabolism. However, some forms of life might exist in dormant states that could potentially survive such extended journeys, particularly if protected within the interiors of larger objects. The contamination of interstellar objects by terrestrial life during their passage through our solar system presents both opportunities and challenges for astrobiology. While such contamination could confound searches for indigenous biological materials in these objects, it also demonstrates how life might spread from one world to others through interstellar transport. Understanding and controlling such contamination will be crucial for future missions designed to study the biological potential of interstellar visitors. The development of life detection techniques for interstellar objects represents a new frontier in astrobiology research. Traditional approaches used for studying terrestrial extremophiles or searching for life in our solar system may need to be adapted for the unique challenges posed by these distant, fast-moving targets. New technologies for rapid biological analysis and remote detection of biosignatures will be needed to take full advantage of future interstellar visitor encounters. The possibility that interstellar objects could transport biological materials between stellar systems also raises important questions about planetary protection and contamination protocols. If these objects can carry life between stars, then special precautions might be needed to prevent contamination of Earth by potentially harmful extraterrestrial microorganisms. Conversely, preventing contamination of interstellar visitors by terrestrial life will be important for preserving their scientific value and preventing biological contamination of other stellar systems. The study of 3I Atlas and other interstellar visitors is thus opening new chapters in astrobiology research, providing fresh perspectives on the distribution of life in the universe and the processes that might connect living worlds across the vast distances of interstellar space. While definitive evidence for biological transport by interstellar objects remains elusive, the growing understanding of these cosmic wanderers continues to expand the realm of possibilities for how life might arise, survive, and spread throughout our galaxy. As we near the gentle conclusion of our exploration of 3I Atlas and its cosmic mysteries, it is time to weave together the many threads of discovery and understanding that this remarkable interstellar visitor has provided. In the quiet contemplation that comes at the end of a long journey, we can begin to see how this single object has expanded our perspective on the universe and our place within the vast galactic community of wandering worlds. The story of 3I Atlas is fundamentally a story about connection the deep. Invisible bonds that link stellar systems across the galaxy through the exchange of matter, energy, and perhaps even life itself. This small, fragmenting object has traveled for eons through the darkness between stars, carrying with it the chemical signatures of distant worlds and the accumulated effects of processes that occur nowhere else in the universe. Its brief passage through our solar system has provided humanity with a direct sample of the interstellar medium and the objects that populate the spaces between stars. The fragmentation observed by Hubble has taught us that the universe is far more dynamic and interconnected than we might have imagined. The breakup of 3I Atlas demonstrates that even the seemingly stable structure of small bodies can be profoundly affected by the long journey between stars and the encounter with new stellar environments. This fragility reveals the delicate balance between the forces that hold objects together and those that drive them apart. A balance that shapes the evolution of matter throughout the galaxy. The scientific investigation of 3I Atlas has exemplified the collaborative nature of modern astronomy, bringing together researchers from around the world to study a phenomenon that no single institution could have understood alone. The rapid sharing of observations, the development of new analytical techniques, and the construction of theoretical models have all contributed to a growing understanding that transcends national boundaries and institutional affiliations. This way, the study of interstellar visitors mirrors their cosmic journey, connecting distant places through the patient work of dedicated individuals. The mysteries revealed by 3I Atlas have also demonstrated the importance of maintaining wonder and curiosity in the face of the unknown. Each surprising observation has challenged existing theories and forced researchers to expand their thinking about what interstellar objects can be and how they behave. The willingness to question assumptions and embrace new possibilities has been essential for understanding this enigmatic visitor and will continue to be crucial for interpreting future discoveries. The implications of 3I Atlas extend far beyond the study of a single object to touch on fundamental questions about the nature of the galaxy and the processes that govern the formation and evolution of planetary systems. The fragmentation of this interstellar visitor has provided insights into the strength and structure of materials that have been processed by the harsh environment of interstellar space. These insights inform our understanding of how matter cycles through the galaxy and how the chemical elements essential for life are distributed between stellar systems. The observations of 3I Atlas have also highlighted the remarkable capabilities of human technology and ingenuity in studying the cosmos. The ability of the Hubble Space Telescope to detect and monitor the fragmentation of a small object billions of kilometers away represents one of the pinnacles of human achievement in observational astronomy. The sophisticated analyses required to extract meaning from these observations demonstrate how far our species has progressed in developing tools and techniques for understanding the universe. Perhaps most profoundly, the study of 3I Atlas has reminded us that we live in a universe of constant change and evolution, where objects formed in distant stellar systems can journey for millions of years to visit our cosmic neighborhood. The galaxy is revealed not as a collection of isolated islands, but as a dynamic system where matter and energy flow freely between stellar systems, creating connections that span vast distances and enormous timescales. The case of 3I Atlas also illustrates how scientific discovery often proceeds through unexpected observations that challenge our preconceptions. The fragmentation revealed by Hubble was not predicted by existing theories of interstellar object behavior, yet it has opened new avenues of research and understanding that will influence astronomical thinking for years to come. This pattern of surprise and discovery is fundamental to the scientific enterprise, reminds us to remain open to new possibilities as we continue to explore the cosmos. The brief visit of 3I Atlas to our solar system represents a cosmic gift, a sample of the interstellar medium and the processes that operate in the spaces between stars, delivered directly to our astronomical doorstep. While we cannot physically touch this visitor or bring it into our laboratories, the photons it reflected and emitted have carried detailed information about its nature and history across the vast distances of space to our waiting telescopes. In this way, light serves as the messenger that connects us to the farthest reaches of the galaxy. The fragmentation of 3I Atlas has also served as a meditation on impermanence and change, universal principles that operate from the scale of subatomic particles to the largest structures in the cosmos. Nothing in the universe is truly permanent. Even the most durable objects eventually succumb to the forces of time and change. The breakup of this interstellar visitor reminds us that transformation is a fundamental aspect of cosmic evolution, and that endings often mark the beginning of new phases of existence. As we integrate the lessons learned from 3i Atlas into our broader understanding of the cosmos, we are reminded of the privilege and responsibility that comes with being conscious observers of the universe. Through our telescopes and scientific instruments, we serve as witnesses to cosmic processes that unfold over timescales far exceeding human lifespans. The knowledge we gain from studying objects like 3i Atlas becomes part of humanity's collective understanding of our place in the cosmos and our connection to the larger galactic community. The study of interstellar visitors like 3i Atlas also connects us to future generations of astronomers who will build upon the foundation of knowledge we are establishing today. Each observation and analysis contributes to a growing database of information about these cosmic wanderers that will inform research for decades to come. In this way, our current investigations of 3i Atlas represent not just present-day science, but also a gift to future scientists who will continue to unravel the mysteries of interstellar objects and their role in galactic evolution. The peaceful integration of knowledge about 3i Atlas into our understanding of the universe reflects the patient, contemplative approach that characterizes the best scientific research. Rather than rushing to hasty conclusions or forcing observations to fit pre-existing theories, the astronomical community has taken a measured approach to understanding this enigmatic visitor, allowing the evidence to guide interpretation and remaining open to new possibilities as additional data become available. In the gentle quiet that comes with deepening understanding, we can appreciate how 3i Atlas has enriched our perception of the cosmos and our place within it. This small, fragmenting object has served as a teacher, showing us that the universe is far more complex, dynamic, and interconnected than we previously imagined. Its journey from distant stellar regions to our solar system and its eventual dissolution into space remind us that we are all participants in cosmic processes that connect every atom in the universe to its neighbors across the vast scales of space and time. As we prepare to bid farewell to 3i Atlas and turn our attention to other cosmic mysteries, we carry with us the knowledge and wonder that this remarkable visitor has inspired. The fragments of this interstellar object continue their journey into the outer reaches of our solar system and eventually back into the void between stars. But the understanding they have provided will remain with humanity as a permanent addition to our cosmic knowledge. In this way, the brief visit of 3i Atlas has created a lasting connection between our species and the greater galaxy that surrounds us as we reach the end of our gentle journey through the mysteries of 3i Atlas and the profound questions raised by Hubble's surprising discoveries. We find ourselves changed by the encounter with this remarkable cosmic wanderer, like ancient starlight that has traveled for eons to reach our eyes. The knowledge we have gathered about this interstellar visitor will continue to illuminate our understanding of the universe and our place within the vast galactic community. The story of 3i Atlas is ultimately a story about journeys, the epic voyage of a small object across the galaxy, the patient journey of scientific discovery that revealed its secrets, and our own journey of understanding as we learn to see the universe through new eyes. This fragile visitor from the void between stars has taught us that the cosmos is far more dynamic and interconnected than we previously imagined. With currents of matter and energy flowing between stellar systems across distances that dwarf human comprehension and the quiet moments of reflection that come at the end of profound discovery, we can appreciate how 3i Atlas has expanded our cosmic perspective. Its fragmentation under Hubble's watchful gaze revealed that even the journey between stars can fundamentally alter the nature of cosmic travelers, and that the universe is filled with processes and phenomena that continue to surprise and challenge our understanding. The gentle dissolution of this interstellar visitor reminds us that change and transformation are fundamental aspects of cosmic evolution. Operating from the smallest scales to the largest dot, the big questions raised by 3i Atlas will continue to guide astronomical research for years to come. How common is fragmentation among interstellar visitors? What can these cosmic wanderers tell us about the conditions in other stellar systems? How do they contribute to the galactic recycling of matter and energy? Each of these questions opens new avenues of investigation that will deepen our understanding of the universe and our connection to it. As Hubble continues to monitor the dispersing fragments of 3I-ATLAs, and as future telescopes prepare to detect and study many more interstellar visitors, we are reminded that we live in an age of unprecedented cosmic discovery. The technology that allowed us to witness the real-time disintegration of an object from another stellar system represents one of humanity's greatest achievements in understanding the cosmos. Through our instruments and our intellect, we have reached across the vast distances of space to touch, however briefly, as a messenger from the stars. The collaborative spirit that has characterized the study of 31ATL is bringing together astronomers from around the world to share observations, insights, and wonder reflects the best aspects of human nature when confronted with cosmic mysteries. In working together to understand this enigmatic visitor, we have demonstrated that the pursuit of knowledge can unite us across all boundaries and differences, connecting us through our shared curiosity about the universe and our place within it. The fragments of 3I-ATLAs will continue their journey into the outer reaches of our solar system and eventually back into the darkness between stars, carrying with them the warmth they absorbed during their brief encounter with our sun. As they fade from view and disappear into the cosmic night, they leave behind a legacy of knowledge and wonder that will inspire future generations of astronomers and space explorers in the gentle silence of space. Countless other interstellar visitors are making their own long journeys between the stars, some destined to pass through our solar system in years or decades to come. Each will bring its own mysteries and revelations, adding to our growing understanding of the galactic community of wandering worlds. The discovery and study of 3I Atlas has prepared us for these future encounters, providing the knowledge and techniques needed to unlock the secrets that future visitors will carry from distant stellar shores. The case of 3I reminds us that the universe is far stranger and more wonderful than we can imagine, filled with processes and phenomena that continually surprise and delight those patient enough to observe and study them. In the fragmenting remains of this interstellar traveler, we have glimpsed the dynamic nature of cosmic evolution and the deep connections that link all matter in the universe across the vast scales of space and time. As we drift towards sleep, we can take comfort in knowing that somewhere in the darkness above us, the fragments of 3I Atlas continue their ancient dance through space, slowly dispersing into the cosmic medium from which they came. Their journey, which began in a distant stellar system millions of years ago, has briefly intersected with our own cosmic story, enriching our understanding of the universe and our appreciation for the remarkable processes that shape the cosmos. On its grandest scales, rest well, knowing that we are part of something infinitely larger and more beautiful than we can fully comprehend. The same cosmic processes that created and shaped 3I Atlas also created the elements in our bodies and the world around us. We are not separate from the universe, but integral parts of its ongoing evolution, connected to the farthest stars through bonds of physics and chemistry that transcend the apparent emptiness of space. Let the gentle mysteries revealed by 3I Atlas accompany you into peaceful slumber, where dreams might carry you on your own journey through the cosmic dark, following the paths of interstellar wanderers as they trace ancient routes between the stars. In sleep, as in waking, we remain part of the vast cosmic story that connects every atom in the universe. To its neighbors across the infinite expanse of space and time, good night from Sleepy Scientist.